So yeah, it's a pleasure to be here today. I said came in all the way from London. Boy, my arm's tired. No, this talk is going to be about sort of spectral methods and ways that we can sort of scale them up using deep learning. So spectral methods are just kind of a workhorse method across the computational sciences. So you can use them to solve PDEs. You can use sort of heat kernels or spectral analysis of heat kernels for describing sort of graph and manifold structures. They appear all the time in machine learning, and my background is more in machine learning. Really primarily be talking about spectral learning, which is just any sort of machine learning method where rather than, say, solving things with gradient descent or MCMC, the output of an SVD or an eigendecomposition, some spectral decomposition, gives you the result that you're looking for. And primarily the inspiration for this project was kind of some of this classic machine learning work out of the early 2000s that also gets called manifold learning or nonlinear dimensionality reduction. But basically the high-level idea behind all of these methods, I mean, this includes things like isomap, LLE, spectral clustering, Laplacian eigenmaps, all of them with some slight tweaks between them. Basically, you take all of your pairs of data, construct a giant gram matrix that basically just gives you some measure of distance between all the pairs of data using some choice of kernel K. You take an eigendecomposition of this matrix, and then each eigenvector of this matrix gives you one dimension of an embedding. So sort of a nonlinear generalization of PCA, and can do very nice things like this unrolling of highly nonlinear high-dimensional data sets into some low-dimensional data set, into some low-dimensional space. However, in machine learning, since we mostly care about generalization to new data points, one thing that's really kind of the Achilles heel of these methods, one of the reasons that they've kind of fallen by the wayside, is that you have to use the what's called the Nystrom approximation to generalize to new data. And that means if you actually have a new data point x and you want to map that to some embedding u, you basically have to take the weighted average over the entire training set of all of the embeddings of all the different points and evaluate the kernel between these points for all of them. So clearly, as your data set scales, first off, just constructing this enormous gram matrix won't scale, and also even generalizing to new data points will scale pretty poorly. And it's also very hard to build in sort of any structural priors, things like translation invariance or things like that. So what we aim to do with this, what we're calling spectral inference networks, is can we overcome these limitations by doing these spectral decompositions using a parametric function approximator by using deep learning. And maybe another motivation for this is that quite a lot of the kind of excitement in deep learning and machine learning in the last 5-10 years has been taking sort of old ideas from machine learning and sort of throwing a neural network in there in some place. So if you are doing reinforcement learning and you have you're approximating your policy or your value function with a deep neural network, you're doing deep RL, which we'll hear about from Sergey Levine. If you're doing variational Bayes and you're approximating your posterior with a deep neural network, you're doing a variational autoencoder. But even though you have deep RL and deep Bayesian models, we still don't have deep spectral learning until now. And so there are some reasons for this, which is that actually doing a spectral decomposition by SGD is quite a lot harder than other methods because of the constraints when you start looking at a spectral decomposition as an optimization problem. So kind of the starting point computationally for turning a spectral method into an optimization problem, the sort of thing you could just do by gradient descent, is this the Rayleigh quotient, which is basically if you're trying to compute eigenvectors of the matrix A, you either minimize or maximize this ratio of this quadratic form of A with the norm of the vector u. So you can see, you can also express this in constrained form here as say, you want to minimize this quadratic form under the constraint that your vector is unit norm. So we have the constraint in blue, and then this kind of green ellipse is the quadratic form you want to minimize. You can generalize this to multiple eigenvectors in this form. So basically, each column of u now is one eigenvector. And so you can either do it in this unconstrained form, where you're now taking a product of a matrix and a matrix inverse, or again in this constrained form, where now These vectors all have to be orthonormal. But to do this in the case where we're able to generalize to new data points, implicitly we're not just trying to compute eigenvectors of a fixed matrix. What we're really trying to compute is eigenfunctions of some operator, and your training data is basically just giving you samples from these functions. So what the problem we're actually trying to solve is to generalize from a vector space to a function space. So we replace this matrix A with this choice of kernel, that, the kernel that defines either your embedding algorithm, and by taking the expectation over your data distribution, this kernel induces this linear operator. And so just replacing all of the sums in your in this quadratic form with expectations, our loss function takes this form here, where we're trying to minimize the trace of this matrix that is an expectation over pairs of data points under the constraint that that our features are uncorrelated. So the idea here is that we're just going to drop in some neural network for U and minimize this quadratic form under the constraint that our features are uncorrelated. So spectral inference networks are an algorithm for solving this. It's an algorithm for end-to-end learning of the eigenfunctions of any linear operator. You start to encounter problems because of this constraint on the expectations. It's very hard to optimize this just from mini batches. So we use bi-level or 2 time scale optimization so that we can actually handle this from finite mini batches. And also we actually want to get an ordering on the different eigenfunctions. So the first output of this neural network is the smallest eigenfunction. Second output is the second eigenfunction, and so on. And so we actually derive a closed form expression for a custom gradient that allows us to do this. So another way that, as I said, you can sort of write this expectation either as a constrained objective or as an unconstrained objective. If you write it in this form, we see it's actually a product of an expectation and the inverse of an expectation. And this is a lot nastier than the kind of typical problems you encounter in stochastic optimization. Because if you just estimate this from mini batches and then take the inverse of this matrix, you'll get a biased estimate. So I'll just clean up the notation here so that it's not just an entire screen full of equations. But basically, we say the constraint on the covariance of the features is sigma, and then this quadratic objective is pi, and then our objective is just to minimize this trace of this product. And the gradient, if you estimate it from mini batches, has this form. We can plug in mini batches for pi, and if we had the true sigma, we could still have an unbiased gradient. But basically, if we just plug in a moving average for sigma and the Jacobian of sigma, we're able to get a much lower bias in our gradients. Now, this sounds like just sort of a nice heuristic, but actually, if you're very careful about your learning rates, then this actually becomes an instance of what's called 2 time scale optimization, and there are actually guarantees on convergence. So people have used this for training GANs as well. This comes up, the sort of original analysis of 2 time scale learning was actually for actor-critic methods. So there are all sorts of problems in machine learning where this comes up. Anytime you basically have 2 coupled objectives where the optimum of one depends on the optimum of the other, these kinds of 2 time scale learning help. And to actually get ordered eigenfunctions, so you don't just get an embedding that's invariant to rotation, but you actually want each dimension of your embedding to, in some sense, be meaningful, a bit like PCA, where your first principal component is different from your second principal component, and so on. We rewrite this objective in a symmetric form by taking the Cholesky decomposition here, and then if we were at the true solution, lambda, the objective written out in this form, lambda would be a diagonal matrix of eigenvalues. And so the forward pass would look sort of like this, where each eigenvalue only depends on the lower eigenfunctions. If on the backwards pass, we basically zero out the gradients going from higher eigenvalues to lower eigenfunctions, this imposes an ordering on the features. And so this actually means the first dimension of our embedding will be the lowest eigenfunction, and so on. And rather than having to write out an entire Cholesky decomposition in PyTorch or TensorFlow and put in stop gradients by hand, you can actually compute this entire mask gradient for this entire matrix in closed form. So you don't have to understand the exact form here, but just know that this can be implemented in a few lines of code and plugged into your favorite automatic differentiation package. And so as basically a sanity check, we looked at the Schrodinger equation, basically just for a single hydrogen atom in 2 dimensions, not because this is a challenging physics problem, but just because we can solve it in closed form. So it's a very strong check on the correctness of our method. And actually, if you, I think I don't have the example here of it failing on small mini batches if I don't use this correction to the gradients. But basically, it fails miserably with the small mini batches, but correctly gets, it doesn't just minimize the loss, but actually correctly gets the different values of different eigenvalues, which shows that the zeroing out of the gradients is working correctly. And if we don't make this correction, then the actual form of the functions that we learn looks like garbage, but it nails it pretty much exactly if we do use this correction. Now that's a fairly low-dimensional function. You can solve it not in closed form or just on a 2D grid, but going to sort of a higher dimensional function space, like the space of images or the space of videos, where you're trying to learn functions over all of pixel space, you start learning some interesting things. So this is an example on a synthetic video data set where we just have 3 different balls inside of a box bouncing off of each other, sort of ricocheting around. And we want to learn features from frames of this video. And so the kernel we're using here is basically just to minimize the squared difference between frames of our embedding. And what we're showing up here is a heat map of the different ball positions for each of the different features that we learn for each of the different eigenfunctions. Most of these kind of look like Fourier modes, which is what you would expect from a spectral method. But then you get something here where the heat map isn't really informative. But if you zoom in, kind of look at which frames either maximally or minimally activate this particular output of the network, you see it's encoding a very interpretable feature, which is either all of the balls being down in one corner or one ball being in the corner and the two other balls being in the other corner. So I think this shows really the advantage of imposing this ordering on the function, on the eigenfunctions, because the individual dimensions of this embedding actually have some, arguably, interpretability to them. And we also look at some reinforcement learning applications, but I think I'm running a little low on time, and that's probably less interesting to this audience. But basically, this is also interesting to people in reinforcement learning, because if you look at the eigenfunctions of the transition operator, that can be used as a learning signal for sub-goal discovery, what are called eigenoptions. And people have tried very heuristic ways of learning these, whereas what spectral inference networks gives you is actually a correct way of learning this. So we think we do a much better job than other people of learning these. But basically, the future directions we want to take this, the Achilles heel of this method at the moment is that you have to track a moving average of the entire Jacobian of the network. But we have ideas of how to remove this and scale things up to maybe learning hundreds of embedding dimensions. We want to do more of a quantitative comparison for more of the reinforcement learning examples. But also, I think for this audience, since spectral methods are so core to so many different problems in physics and engineering, I think there are lots of really exciting applications there. So I'll say thank you.
Thank you.